Start, right?
Yes, sir.
Boy, we're thin today. I don't know if we lost people or what. Anyway, did you all get the homework up there?
Yes, sir.
Everybody sit. Now, I want to, well, I'll do it the standard. First, are there any questions before I start? Any questions at all? Everybody have a chance to get this book or a PDF of it done? All right, make sure that you keep up with this. This stuff will get you, of all the classes I've ever taught, this one is the one that loses people quicker and faster. More people flunk this course than any course I've taught, as far as I know. I mean, it wouldn't be surprising if like 30%, 40% fail. That's the reason I'm trying to encourage you. I mean, if you know what I'm talking about here, because this is a difficult conceptual course. So I'm just trying to keep you aware of how important it is to do this. Now, for the homework was fairly straightforward and easy, but by the same token, if you don't do it, you think you can get it on Thursday night, you're dead. I mean, I can't be more clear about this. So, questions? Did you have one?
1.23.
Okay, help me out with that.
I will read it. Or,
Yeah, it's let's see. Which one did you want? Just like all of them?
1. The last one.
The last one?
Yeah.
1.23?
Yeah.
Well,
So-
we're going to do several of these. They're all, I chose these problems because they expose a lot of the concepts that people confuse. All right. So this is 1.23. Go ahead.
A comic strip made the following statements.
Yeah. I know this one. Weather, rain, right?
Mm-hmm.
Yes.
So on Saturday, the percentage of rain, what is it, 60% chance of rain?
Yes.
Right, chance of rain. Okay, go ahead.
The second one was Sunday. There's a 40% chance of rain.
So 40% chance of rain.
And that's S2. Saturday is S1. Sunday is S2.
What's that?
It says at the end in parentheses denoted as S1 or denoted as S2.
Oh, this is S1?
S1.
Okay, S1 and S2.
And then, so the claim is there's a 100% chance of rain for this weekend.
Is it true or false? All right, here's the crazy thing about this. If these are mutually exclusive events, if rain on Saturday has nothing to do with rain on Sunday and vice versa, then we can do this problem in a very analytically correct way. And it's the same type of problem where if there's a 60% chance of rain, there's a 40% chance there isn't rain. Y'all follow me on this? Now, if you think about this, and I just want you to just think about this for a second. Go through it in a binary fashion. We have 2 days. We could have rain on either day or no rain, right? So there are 4 possibilities, right? There could be no rain Saturday, no rain Sunday. There could be rain Saturday, no rain Sunday. There could be no rain Saturday, rain Sunday, or there could be rain both days. Do y'all follow me? Now, if it's mutually exclusive, and this is the problem with this problem, there's nothing he talks about with weather forecasting and prior days' behavior have to do with future days. And so when I looked at his analysis and he says, yeah, it could be true, I'm thinking, how? I mean, because he's saying that here's the statement that's made at the end. There's a 100% chance of rain this weekend, or that week. Y'all with me? Now, the obvious thing is a mistake. This is the mistake. At least you could see somebody that is unschooled doing, well, 60 and 40 is 100. It's a 100% chance. That would be completely wrong. Y'all with me? So we're going to do it. I'm going to do it the standard way, and we'll discuss all this stuff, you guys. And I did put the solutions, didn't I? I posted.
When did you post them?
There was some of them. It wasn't
there's
last
some.
night, I think.
Every problem I assign, there's a solution.
Okay.
Isn't that right?
I saw it through like
Every single problem I
Okay.
there's a solution.
There's most of them.
I do see.
There's most of them, but not all.
Yeah,
Of
I do
the
see
ones I
1,
assigned,
2,
isn't
3.
there? Or the first ones, because we did them, I think, right?
We did the first
I think we
ones in
did
the
the
class.
first question.
So you did 1, 4,
We did
1,
1, 4,
5,
All right,
1,
we'll
8.
do it. If you want, I'll post them all if I can.
Yeah.
So you-
All right, I don't mind doing this at all. What I'm trying to do is get you to work them.
Yeah,
And
sure.
don't just look at this list. So for this one, here's how I'm going to do it. So if there's for this part, if there's a 60% chance of rain, there's 40% chance of no rain. Right? And for this one, if there's a 40% chance of rain, right, there's 60% chance of no rain. Okay. Now, think about, let's do it this way. 1 is rain, 0, no rain. Okay? My possibilities are 0, 0, 1, 0, 1. I mean 0, I should say 0, 1, pardon me, 0, 1, 1, 0, and 1, 1. So I'm going to look at this one for now, because if you're taking if we're looking for the chance of rain over the weekend, let's first start talking about the chance of no rain, because 1 minus that will be the chance of rain. That's my thoughts on this one. So for this one, this probability of this event of no rain is going to be equal to, well, I'm assuming they're mutually exclusive, so it would be 40% times 60%, or it would be 0.4 times 0.6 would be the probability of no rain over the weekend based on if they're mutually exclusive. Do you all agree with that? And that is what? 0.24, is it? Correct? Now, what does that mean about the probability of rain? Well, that means the probability of rain would be equal to 1 minus 0.24, or about, it would actually be equal to what? 0.76, or about 76% chance of rain if they're mutually exclusive. Now, in his discussion, did you read this discussion on this one in the first part or not?
In the textbook?
In the solution that I posted.
I didn't know there was.
I promise you I posted them there.
Ah, yes, sir. I'm looking at it.
You see them? All right, what does he say? He says, well, they could be what? Conditional. This is against everything that I know. I'm not a weather forecaster, but generally speaking, prior weather has nothing to do with future weather in terms of an event happening or not happening. When you get, by the way, this is kind of crazy about weather forecasting. When they said there's a 40% chance of rain in the first hour, and then 60% chance of rain in the second, and then 70% chance next, and then 50, all those events are mutually exclusive. You don't sum those things up and say you have to have one. Do you all follow me in this class? And that's the biggest problem with weather forecasting, because you can get confused. Go
I
ahead.
always thought the percentage of rain was the covered area, the percentage of the area.
A chance of rain. He's talking about the chance of rain is that much. Now, you want to know how they actually calculate that or estimate that? There's about 5 things. I lived with a guy who worked for AccuWeather at Penn State. He graduated in meteorology. His name is David Decker. So there's 3 things that you have to worry about. First is past history. They look at the past history. I'm just going to mention this about weather forecasting. It's kind of neat the way they do this, because it applies to really all sorts of ways we estimate things in the world. First, they take a look at the atmospheric conditions in, you could say, almost like a convolution type of problem. In the atmospheric conditions in the past couple of days and the conditions present, all right? And it has to do with the season and so forth. If you take a look and say 25 years ago, the exact same humidity, wind conditions, and surrounding area temperature patterns were there, and not just 25 years ago, but say every time that happened, there's a 99% chance of thunderstorms occurring now, and there's a front moving. So they look at the past history and they predict the future based on past. That's the first way. Second way is called the actual deterministic model, and that's where the atmospheric conditions, they have models. Now, if you look at hurricane models, you're going to see a whole lot of divergence in paths. Now, that's based on what kind of model they're using. So this is the compressible fluid models, where they model the airflow, they model the heat, they model the inputs, because they know about how much energy the sun's going to put in and all this. It's fairly complicated. And they figure out the dynamics. Now the Earth's moving, there's Coriolis force, there's all this other stuff, but they can figure out the likelihood of actual precipitation occurring or whatever the event may be. And they have a that's a deterministic, it's a forward solving. Then there are models that use both. All right. But in all these models, the level of uncertainty has a great deal to do with the known data, how accurate they know the data. And the problem is, I'm leveling with you about this. I'm not the guy that knows, but my roommate did. And the real problem with this is, if you want accuracy, you have to have extreme knowledge of the temperature variation all over, the humidity conditions. You have to know a whole lot more than they know. They estimate things and they assume things. And that's why there's so much uncertainty. Weather forecasting more than 3 days away, I think, is still just about a coin toss, unless you see like a hurricane coming or you got some definite thing. You just take a look at this. After 72 hours, it's almost impossible with any certainty to know what's going to happen. Anyway, read the first part of the problem. He wants to know, evaluate the statement if there's a 100% chance of rain, right? Is it possible? Correct? Okay. All right, now, in there, if you look at the answer, he says, if these things aren't independent events, that's possible. Do you see that in the solutions? I forgot the wording.
Statement S3 can be true. The probability of rain this weekend can be 100%.
Listen.
For example, and then it explains the probability of both S1 and S2. So this happens if S1 and S2 are disjoint if it rains on Saturday or Sunday, but not both.
Wait a second. Oh, not both. Okay, I see. Okay. Go to the last. What is the last part on that problem? Because this is one that's a little confusing, and he didn't really go into the details in the chapter.
The last part C? Or part
Yeah,
B?
part C.
When S1 and S2 are independent, the probability of S1 and S2 being, what's the
Intersection.
Yeah, intersection equals 0.24.
That's no rain.
That's no rain, and then therefore the probability of it raining is 76%.
Yeah, and that's the right way to do that problem. You cannot assume, all the other stuff is based on a conditional probability that one is going to be dependent on the other, and that's impossible. I mean, in my opinion, with weather, you can't, if rain happens today, it has nothing to do with if rain happens tomorrow. Well, maybe it does, but that's not something I really want to talk about. That whole problem is meant to have you recognize that these things, the common mistake is add them up, it's 100% chance. That's the common mistake. That's the mistake you never make, all right? What you should do is let's assume that they're independent. One is not dependent on the other. Then you'll always find what can happen. You can have rain or not rain. So 1, really 0, 0, 0, 1, 1, 0, 1, 1. And only one you need to do is find out the probability of no rain, which would be the first one. 1 minus that is the probability of rain. That's the bottom line, because then that's two things. Go ahead.
It's almost like the link problem.
It is exactly the link problem, only without the word link, all right? Because now you need to figure out the probability of it not occurring, and 1 minus that is the probability.
Could you almost draw it like a link if they're two parallel?
Yeah, you could if you wanted to. But he puts it in words to make you think. Now, what is 118 in that?
118 is the link problem.
Did you all do this one? How many did it? Just be honest. Okay, if you didn't do this, please work with me. Did you do it or not?
No, I was about to do it. But
All right, we did this basically. It's a very simple link problem. The one is you're probably going to see are more complicated, so you're going to have to understand the way to do it. And I'm not going to give you something where you have to take, you know, the things that where you did where you took Y delta transformations and circuits. Do y'all remember those things?
Yeah.
Or power, whatever. You can do that with link problems, but it gets really complicated because all the stuff, the Y delta you had, is for even or for identical like values for the impedances and stuff. when all of a sudden the probabilities are different, it's a much different kind of problem. It's more involved. Okay. If you want me to go through this entire problem, I will, but I've got to tell you, discuss all the probable aspects. But some of this stuff, honestly, I think will do more to confuse you. Weather-related events are generally independent, completely independent. Okay. With me, 118 is the link. I want to do at least a couple of these. If you didn't do it, please follow me and ask yourself, could I do this? You don't want to get behind in this. All right, so for this link problem, he's going to have a sender and he's got a destination. This is the way he does this. And then he's going to have a link here, and he's going to have this bingo route from here to here. And he should have the flow of the signal goes from S to D. And then he's going to, is this link one, the first one on the bottom?
Link one on the top.
Oh, so this is link one with probability one of working. Link two, probability of two of working, and link three, and probability of three of working. Correct, class?
Yeah.
Yeah.
All right, we want the probability that the system works. Now, based on our discussion Friday, the way you go about this is what? We're going to piecemeal it, and first we're going to try to reduce the complexity. Anything in series we can reduce, correct, class?
Yes.
So we're going to reduce that first. And I can say the entire probability of this link working up here, and I'll just call it L12 is going to be P12, and that's going to be P1 times P2. I hope everybody follows me. Do you agree with that?
Yes.
All right, what's the next thing I'm going to do? Now with link problems, you almost always are thinking, if I got parallel stuff, I'm thinking about it not working. That's the way you should think, right? So down here, another color. The probability of link 3 not working would be 1 minus P3. That's not working. And the probability of this link not working would be 1 minus P12. I've defined P12 as that. So that's the probability of them not working, right? Are they independent?
Mm-hmm.
Yeah.
Absolutely, right? If there was dependency, this would be a different problem. We haven't got there yet, but we will. You with me, class? So if they're independent and you got two events, so that's probability of it not working, that's probability of it not working. I didn't say this last time, but if you're talking about the probability of A, B, means the probability of A and B occurring, if they are mutually exclusive events or independent events, that's simply PA times PB, probability of A times probability of B. That's what it is. Did y'all read the chapter? If you haven't read the chapter, please read through the chapter. He discusses this, and he does use Venn diagrams to explain things. He does, I think it's a pretty good job, but he doesn't show you, quote, engineering problems. Yes, sir.
That was a question. On the quizzes, will you explicitly have us write out a Venn diagram or do an entire sequence of solutions?
I will ask you to do a Venn diagram for
But what about, like, you know how you said he writes out all the sequence of solutions?
No. You don't have to do that, but I'll ask you for a Venn diagram. If I have like A1, 2, B, we'll do this probably.
Gotcha.
B 1, 4, and C say 2, 3, something like that. And I want you to show in a Venn diagram form what it would look like. There's overlap, right?
Yeah.
And then I'm going to say if the total sets are the values included, then what's the probability if we're assuming, say that each value is equally likely with that. But we're going to go through that. All right, so if we have this, but the reason I'm saying this, these are mutually exclusive events, right? So, and again, we could go through the thing. We could have this link working, we could have both links not working, which is the key one. We could have this link working, this link not working, this link not working, this link working, or both links working. The only one we care about is neither link working, because if we have that value, we can subtract that from 1 and get the probability of the thing working. That's the whole concept idea behind this stuff. So for that part, then we say, and this is the probability of not working. And that would be equal to the probability of that one not working, 1 minus P12, times the probability of that one not working, 1 minus P3. And that, if you go ahead and break that out, you have 1 minus P12 minus P3, and then plus P12 times P3. So that's the probability of it not working. You agree with that, everyone? Therefore, the probability of it working, and this is an easy one. Right here is going to be 1 minus this, so it's 1 minus P12 minus P3 plus P12 times P3. And if you take a look at that, that's going to be what? P12 plus P3. P12 is just P1 times P2. And then it's going to be minus P12 times P3. And I think that's the answer. You all follow me on this? This is the only there's no real trick here other than thinking I got to figure out what the probability is if it's not working. One last question for everybody. What if I did this? I'm going to put one here.
You're missing some P's. The minus P1. Oh wait, that's never mind.
This is P1 times P2.
Okay, you're good.
Sorry. The only reason I did that is it's just a simple shorthand abbreviation. Okay. Now, and this will work, but this is the one part I wanted to ask you. Suppose, and I'm not going to get crazy with this stuff. All right. I think everybody sees if I added another link, say P4, P5, and P6 right here, that wouldn't be bad because now we're just going to multiply them all. That's the probability of this working, right? And then they're in parallel, so now I need the probability of it not working, 1 minus that P4, P5, P6, right? And then it would be that times the next one, right? Here. And for not working, and you see the relationship. Here's the tricky part. If they take something like this, follow me?
Mm-hmm.
Now, all of a sudden, this will cause panic. Say P7, something like that, right? How do you do that? Well, we're not doing it this time, but you remember those transformations, delta to Y transforms? Do you remember that when you were doing impedances, right? This is not equal in every sense. The branches, when you did those for Y delta transformations, the Z delta or the ZY was always the same on each of those things. Here, it's not, so you have to write simultaneous equations to get the equivalent. And you would want to take this delta right here, basically. You've got this, this, and this. That delta right there, and you would turn it into a Y. You all hear me?
Mm-hmm.
And then you do it. That's a more difficult thing that comes later. So don't panic if you see that online or if you look at some of the other material, because I think Bashir put up a bunch. I showed you the link to Chan's book, right?
Mm-hmm.
There are other things linked. That problem will be in some of them. That's a more difficult problem. But don't worry about that right here. All right, I want to do one of the other ones. Let me just look here. I got a whole bunch of little notes. I think it isn't 1.5 the one where they want the probability of a head occurring in the nth trial.
Yeah.
Right. And this is a pretty good one because it'll make you think, right? And I'm going to do at this point in time 2, 4, 6, 8, 9. We've got a whole lot more kids. I promise you we do, at least in my role. Is there something going on?
Everybody that's here Monday is here.
Am I wrong about that? Didn't you see a whole bunch of kids in here? I'm going to check now. I'm looking at this. I thought I had like 17 or 18 kids in here.
They'll be here for quiz day.
Well, when they come to the quiz,
Yeah.
I'll find out. All right, so problem 5. You have a book? Can you?
Yeah.
One 5. What?
Do you want one in particular, or just like the statement problem?
Yeah, tell us. I want to talk about it because some people probably hadn't taken a look at this in a hard way. You need to. It's a good problem. So go ahead.
Sure. A fair coin is flipped until a head appears. Let the number of flips required be denoted by n.
Okay. So n.
The head appears on the nth flip.
That's where head appears. Okay.
Assume the flips are independent. Let the outcomes be denoted by k. The event n equals k means exactly k flips are required.
Yeah, and this is the thing. Some of this wording can confuse people. I promise you can. So what it's saying, if you say p of k, it means the head occurred on the k flip. With me? All right, go ahead.
The event n greater than or equal to k means at least k flips are required.
All right, now he's getting into something where he says p of n, what did he call it? Equal?
Greater than or equal to.
Yeah, he says probability of n greater than or equal to k, right? All right, we're going to go for the first part, and this is p of n equal k, and I'll explain why. So n equal k. So what he's saying is we're going to have he's saying the head occurred on the k1, so they're going to have tails. Matter of fact, let's do it this way. 0 is tails, and 1 is heads. You'll see the binary reason for this. All right? So we have basically this 0, 0, 0, and then 1. And the 1 can occur at any position. But we know one thing. If we're looking at this, and I should mention something about this. This comes later, but I'm going to give it to you. If you talk about the binomial equation in Bernoulli trials, things like this, most of you have had this in some course. If you talk about the ability to take k items in n attempts. All right. What this implies is how can you get 3 tails in 5 tries? Okay, that's the probability. With me on this now? I'm trying to explain this in a very simple way. And if somebody can help me explain it, please do so. So this is something you're going to see all the time in this course. Now these are something, they're absolute decisions. It's one way or the other. If I have k trials, the k trial either happens or the event happens, however I define it. Heads or tails. It's the only 2 possible outcomes. And we have n attempts. This is equal to n factorial over k factorial times n minus k factorial. And then p is the probability of the event occurring, whatever event we're talking about. It would be to the k power. And then 1 minus p, it would be to the n minus k power. Now, this will give you, and by the way, if you sum all the possibilities of this, you get 1. That's another. For all the probabilities, it has to sum to 1 all the time. So if you take a look at this problem, the way he structured it, we want the probability of tails occurring in the k, and this is the kth event right here. I'm going to say this would be the kth event. Then we want all zeros in the k minus 1 event. You all with me on that? All right, so here's what I'm going to do. We're going to go here and we're going to say that means the p, and we want zeros in k minus 1, so it's going to be k minus 1 events, right? And if we just take a look at this, what we can do is take this and we'll assume that we have k minus 1 events. I want to do it this way. What I'm going to say is, what is the probability or possibility of getting all zeros up to k minus 1? Then I'll deal with the last part in a second. With me, class? All right, well, this particular one is going to be, well, since n and k in this case, based on this formula, become the same, this is going to be 1. You just have k minus 1 factorial over k minus 1 factorial. And then it's times, since the first item and the second item listed are the same, this n minus k is 0. I hope everybody knows 0 factorial is 1. With me, class? So this is that part. Then I have p, and since it's been, I think it said a fair coin somewhere.
The beginning.
All right, so that means 1/2 would be to the n, or to the k power, which is, or to the power, which is k minus 1. And then the remainder is going to be simply, since these two are the same, it's 0. It's 1/2 to the 0. So I can get rid of this. So this means the first part goes away, and I have, it's 1/2 to the k minus 1. That would be the probability of getting all tails, and I think everybody understands that. It's just multiplying the probability of a tail on the first one, probability of tail on the second, probability of tail on the third, and so forth, all the way to k. So k minus 1, we got all tails. Now he wants a head, right? Well, what's the problem? Yeah.
So wait, to get this, we would have to know that p, k, comma n, probability of.
Yeah,
k.
but in this case, what I'm just doing is all tails out to k. So n and k, or the n here and the k here, denote, this is the number of, you might say, of outcomes you're looking for. And this is, that are either heads or tails. In this case, we're talking about tails. And this is the number of attempts. They're both the same. I just want all tails.
Okay.
And just take 1/2 to the k minus 1 will give it you there too.
Oh, okay, I see. Yeah.
But I was just trying
I
to
got you.
show you the form. So you have this. That's probability of all tails. Since heads and tails have the same probability, if I multiply that by 1/2, then I get the probability of actually all tails and a head. With me? So if I multiply this by 1/2, now I get the probability. And if you notice what that does is what? It just puts it 1/2 to the k, doesn't it? So that means the probability right here of n equal k is going to be 1/2 to the k. I think he has that. Does he have that in the solutions that I posted? He does or not? Did you see it? Did somebody look at it?
Yes.
He does? Okay, I want to make sure it's there. Sometimes I think the solutions omit certain things in steps. I want to make sure you see. You all see this? All right, now that's n equal k. Now what's the next part? That's the right value. So it's the probability of all tails and then a head on the kth toss. Okay, go ahead.
Let's see. Show the probability sum to 1.
Okay, now I got to do something here. This is a good time for me to do this part too. First, please write this down somewhere in your notes. This is real important. We'll be using this all the time. And this is, because it doesn't have to be equally likely probability. You have two possible outcomes. It could be 30% chance of the right ones, and it could be basically 40% or 70% chance of the wrong one. And then if you want to know how many outcomes that are considered positive occur out of, say, 3 positive outcomes, 5 attempts, you can do this, it'll give you the right answer. So now before I get into exactness of that one, I got to show you this. This is geometric theory. It's basically geometric series, but it's summing, and this is so important. You're going to be responsible for knowing this. I show people the trick on this one. If I say, I'm just going to call it P, is equal to a summation. Let me do it this way. No, I'll call it P is a summation, and it's going to be from, say, K equals You can do it from anywhere to anywhere. I'll say Q1 to Q2 here of A to the K. So what I have here is something, it's a geometric series. I'm trying to put, well, I'll tell you what. No, I'll leave it like that for now, okay? I'm going to just leave it. So what does it mean? Basically, this is equal to A to the Q1 plus A to the Q1 plus 1 plus plus, and it's going to be A to the Q2 here. You all with me? I'm just showing you. Now below it, I'm going to say I'm going to take A times P, which is going to be A times that summation, K equals Q1 to Q2 of A to the K. I'm going to write it out. So here I'm going to have A to the Q1 plus 1 plus A to the Q1 plus 2 plus plus A, and this is going to be to the Q2 plus 1. I hope you all see. I'm just trying to show you I've taken this value and I multiply by A and I get this. There's nothing tricky here, but I want to show you the reasoning behind it. Go with me. Now I'm going to subtract this. I'm going to take P minus AP. And if you look at this, so I'm going to have 1 minus A times P. Now, what am I going to do? I'm going to put a negative sign here, and I'm going to subtract those. Y'all with me? Follow me? All right, well, Q1, A to the Q1 exists here, but not down here. So A to the Q1 exists. And then, as I'm subtracting, all these other terms cancel except for this one. So it's going to be minus A to the Q1, Q2, pardon me, Q2 plus 1. Can you all follow me what I've done? This is standard. You had this in your mathematics courses and series analysis. Matter of fact, there's so many ways to do these problems. This is just one trick. All right, now if you have that, if you want P, you divide by 1 minus A. So that means this entire sum right here, write this down, from K is equal to Q1 to Q2 of A, right there, to the K. That is equal to A to the Q1 minus A to the Q2 plus 1 over 1 minus A. Just remember that. And let me show you the way a lot of times people remember doing this. In general, if you have a series where you're going from K equals 0 to infinity of A to the K. Now this is a geometric series where we're going from 0 all the way to infinity. With me? What that's going to be is simply, since K is 0, it would be like Q1, this is going to be simply A to the 0 or 1 over 1 minus A. Right? I want to, and then I'm going to show you one other thing, because these are the ones that occur so commonly. If you take a look at that, and then you realize if I want the sum from K equals 1 to infinity of A to the K, now this one started at 0, right? So if you think about this, that's really going to be A to the 0, which is 1, right? Plus A squared. So if I take this value here and I subtract 1, I get this value. Just think about it. So if I take 1 over 1 minus A minus 1, now I get this value. And you'll see why I did it. You all with me, class? Because for this one, you get the first term, K equals 0. Well, A to the 0 is 1, right? I made no restrictions that A had to be less than or equal to, or less than 1. But in fact, for these series where the end is infinite, the magnitude of A can be complex, has to be less than 1 for it to be convergent. Otherwise, it's divergent. It'll blow up to infinity. Now, why did I do that? Well, now we come back to the problem we were talking about. Remember that. That's a valuable thing. Do you all remember seeing that before now?
That?
Yeah.
Nah.
Well, this isn't in your math courses. This is just general series analysis.
Just count two.
Time ago.
You had
Yeah.
geometric series. You have, you remember McLaren series,
Maybe.
all those things, right?
Yeah.
Binomial series. These are just ways of evaluating any kind of series expansions of things. And a lot of times the limits aren't infinite. So, somewhere I had the probability of n equal k, or k equal n, was equal to 1/2 to the k, right? Now he wants to show, remember, that's a head occurring on the kth event. So if it was the first event, right? Or I'm sure, you can't have the 0th event on this one. It can't be k, because there's nothing occurred. You all with me? On the first event, it'd be 1/2, then 1/4, then 1/8, and so forth, right? So he wants this sum. Here, our a is going to be 1/2. And he's looking for what is the sum of a to the k, where k goes from 1 to infinity. That's the value he wants. Y'all follow me on this, class? He wants to show that, this is the probability of all tails, but you get a head on the kth event. So if the kth event's 1, the probability of a head or a tail in the first event would be 1/2. Makes sense. Probability of a head or a tail on the second event would be 1/2, right? But if you wanted tail, it'd be 1/2 times 1/2, right? Then 3 tails and a head, 1/2, 1/2, 1/2 times a head. Y'all follow me on this one? So this thing better sum to 1, or we've messed up. Remember what I showed you here. RA is 1/2, right? I try to make sure you see the link between that and this. It's identical. So if I take a look at this, I have 1 minus a, 1 over 1 minus a, and it's going to be minus 1. Now put in the value for a, but it doesn't, you could do this so many different ways. You can get a common denominator, multiply by 1 minus a, 1 minus a. But what happens here? I have 1 over 1 minus 1/2, right? Minus 1, and that is 1. Look, 1 minus 1/2, it's going to be 1/2. 1 over 1/2 is 2. 2 minus 1 is 1. In fact, it is. That checks that box. I wanted to make sure I showed you that summation right there, because you use it a lot. Do you remember when you had, didn't you use that a lot for Z-transform? How many had Z-transform? You had
Z-transform.
You had
We
signals and
didn't get
systems.
there.
Huh?
We didn't get there. We didn't get to any discrete.
You have to do Z-transform.
We didn't get there.
In Yinsen.
Z-transform?
You have
I
to
remember
do it.
Z-transforms.
If you didn't get it, you're going to need it a lot, because what Laplace transforms, remember, if you think about Fourier transforms, right? You had Fourier transforms, Fourier series, and then you had the DTFT. Do you all remember the DTFT? And then what? For Laplace transforms, the discrete form of the Laplace transforms is the Z-transform. And the Z-transform is very powerful. It allows you to do all sorts of stuff. If you haven't had it, you're going to need it, I believe. I mean, I don't.
We just didn't get, we didn't have enough time.
You gotta have enough time. Well, anyway, we'll figure that out.
Yeah.
Anyway, you use this type of stuff all the time for Z-transform analysis. Okay. So it checks the box. What else did they ask?
What is the probability that n is greater than or equal to L for all L greater than or equal to 1?
Okay. So this is an interesting. And you have to start interpreting what he's asking. Remember, the probability of an event occurring, the definition here, on the kth trial is this, right? Now he's saying, what is the probability?
Like the K trial is greater than 1. Like
No,
there's
it
greater-
can't be greater than 1. What is he saying? Of the value L, right, being greater than, well, how does he write it actually? Probability of what?
N greater than or equal to L. For all L
Greater than or equal
to 1.
to L? Go ahead.
For all L greater than or equal to 1.
Oh, okay, yeah, all right. So what is it really asking? Now that's the hard part. Think about it just for a second. If we have N equal to L, right? Then we could have N equal to L plus 1. You follow me on this? I want you to just think about this, reason through it. He's saying, what is the probability that N is greater than or equal to L? L, think of L as a value, 10, all right? Well, what is the probability of N equal to 10? 1/2 to 10, right?
Yeah.
What is the probability of, now we go N equal 11, of 11, right? Right,
Yeah.
being greater, plus 1/2 to the 11th. You with me? So what is he really asking for this one? It's the interpretation. I wish I had it, but I'm not expressing this as clearly as I'd like. But what he's saying is, if this is the value of, or the probability of the hit occurring at like the 10th try, think of that as a solid number, 10th try. He wants the probability that it would be equal to, or the try would, or the probability of the event occurring at the, not just 10th, but the 11th, the 12th, the 13th, all the way to infinity. Now that's the reason that series thing is nice. So what am I going to do? The probability of N greater than or equal to L. It's always interpretation of what he's asking for these kind of problems. That's going to be a sum, right? And it's going to be what? Well, we know it's going to be 1/2. I'll just leave it as A, right? I'll put it to the K. But where does it start? K starts at what? L, and it goes to infinity. With me?
Yeah.
So what's that? Now, I don't know if he does it quite like I'm doing, but this is the idea. So this is going to be what? Do you remember from before? Did I put it up there? There it is. So my bottom one is L, so that's going to be A to the L minus, well, the upper limit is infinity, so I don't need that, over 1 minus A. Do y'all follow me? It's right here. Can y'all see that? All right. A is 1/2. I put it as A just so you see how it relates directly to that formula. So what's this going to be? A, or 1/2, pardon me. 1/2, and it's going to be to the L over 1 minus 1/2. Now, you can mess with this. So that's really 2, isn't it? So it's 2 times 1/2 to the L. And here's where you can have fun. That's the correct answer. Do you agree with me? But I can factor out a 1/2 and get rid of that 2. And so this would be 1/2 to the L minus 1. Now, does he have that answer? I forgot which answer.
The answer's okay.
Which answer does he have?
For C. Or for D.
Yeah, I got it up to date. So, yeah, he has 0.5 to L power over 1 minus, in parentheses, 1 minus 0.5, and that equals to 0.5 to the L minus 1.
All right, that's what we.
That's what you got.
Yeah, but I want to tell you, see, this is the correct answer too. Right? Do you follow me? There's different ways to render this, but sometimes it doesn't click that what you got is that. I'm just loving with you. I see this stuff. I've taught probability a couple of times. I think I taught it last summer, the summer before that. Long ago, I've taught probability. I use a lot of this stuff in radar, but I don't, I mean, this kind of stuff, this is kind of silly. It's all applications to stuff of detecting targets and classifying targets, things like this. But this is very good to make sure you're clear about the fun. It's very easy problems, yeah.
I understand the answer, but I'm trying to understand like where is this like applicable? Like would it only be applicable when you're given a number of trials? Like
Here's the thing for me. All right. I'm looking at the probability that I shoot down a target,
Mhm.
all right, just have a direct hit on a target in n attempts. All right. Well, I'm looking at no hit, no hit, no hit, no hit, hit. All right. I have a probability of a strike and a probability of a miss. And these things are, even the probabilities change with time as the target's moving closer and closer. Trust me on this one, it gets really complicated. So really what I'm looking at is, and this is something we'll talk about, the estimated number of times, this comes further down, that it takes before I have a 90% likelihood of hitting that target that's incoming. So now I go through and I sum the, first I write an equation for the probability of striking it on the kth time, all right? If it's, say it's 1/2, it would be 1/2 to the k, with me?
Yep.
Now I want to know if that's the probability, and it can be very low, by the way, for some of these things. I want to know the probability of striking, or I want to know first the probability of striking it between the kth trial and infinite trial. So I want to figure out that. I know the sum of them better be 1, right? I'm really in trouble. Even at the end of the day, if I take 1 billion times and I can't knock it down, I got a real problem. Anyway, you go through that scenario and you're going to get an equation like we had basically this. With me? All right. Now what I want to know is the mean value of L. And things like that we're going to get into. If anybody had this course before, or they've had things related to this course, mean, standard deviation, mean squared value, all these things have extreme importance to us in engineering, especially when we're doing things where either process, if you're talking about VLSI process and the actual number of defects and errors statistically being available to you. You got to estimate this. You got to estimate the amount of profit, and all these things get statistical, probabilistic. They're not deterministic. It's not an absolute value, and that's why this stuff is so important. I hope I gave you a little idea.
Yeah.
But these things are important. Now, I think with that one, that's basically what we've done with that problem, right?
Yeah, there's like one for the other possibility where it's like less than or equal to L. And then
It's the same.
yeah,
Okay.
same answer.
You just take
Yeah.
take this and just change the limits. That's
Exactly.
the only thing you got to do.
And then it's like do the previous two parts sum to 1.
No, because what happened? You counted them twice with that greater than or equal to. All right, if it was greater than only, then it would be fine, but it doesn't. And he does mention that. I looked at that. I want to do one other one. I think some of you may not like. Wait a second. This only goes to 11, right?
Yeah.
I'm not trying to, look, I'm trying to tell you one. Only way I know to learn stuff is go through these problems and teach them. Because you're going to find so many ways to mess them up. That if I don't go through and expose what I think are some of the greatest possibilities of failure, I'm not doing justice to you guys. Because I want you to read it and try. But I can't do every problem. I can't discuss every possibility. But hopefully for most of the stuff, you'll get it. All right, I want to tell you 1/6 is the same thing, only now the probability it changes between 0 and 1. Remember that the thing I showed you in there with right here, I showed you the binomial terms, all right, the binomial coefficients. Do you all remember that?
Yeah.
P of n. If you use that for that one, you can do it. I want to do the one with the last, or sorry, 1.7, because that's one we haven't done before. But please make sure you do 1.6. It's straightforward, I promise you. It's the same thing we just did, only now the probability isn't equal. When I had this stuff, it was a senior level course, and we had a much more involved book. It was Larson and Schubert, and I can remember one thing about it. I used to spend hours and hours challenging myself to figure out how certain things could happen. It really got confusing, some of the stuff, at least for me. Okay, this is the one 1-7. I gave you 1-7. Yeah. There's problems I gave you I didn't cover today, but I want to do this one because it's decks of cards. We're going to use decks of cards all the time. So in a deck of cards, basically we have 13 members to each suit. And there are 4 suits. And I think, does everybody know what a deck of cards is? Just all right. You can have clubs. Do you know? You know what cards are? All right. So you can have clubs, hearts, spades, diamonds. Right? There are 4 possible suits. Those are different little symbols on them. And there are a lot of different decks of cards that aren't poker cards. So I'm just saying that because my wife's Chinese, and when you talk about cards to her or checkers, it's Chinese checkers. The cards have a whole different meaning in the general sense. So I got to be careful sometimes. All right, this is American cards. They're just poker cards. So now, go ahead. First one.
Let's see, what is the probability that you get clubs?
All right. He says clubs. That's one of those suits. Right? Probability of club. There's 4 suits. They're all 13 members. There's 52 cards, right? So it's just 1/4. And I'm trying to make it as simple as possible. How many looked at this problem? All right. I'm hoping you're asking yourself things, and hopefully you feel, oh, I got this. This is a stupid problem. I hope it's that way. What's the next one? You'll see you can make mistakes. Go ahead.
Probability of getting a queen.
All right, just the queen. How many queens are there? Well, there are 13 members that go from ace, 2, 3, 4, 5, 6, all the way to 10, and then jack, queen, king. With me? So there would be 4 queens in the deck, right? And probability of a queen would be 4 over the number over 52, or really 1/13. I hope he has 1/13. Follow me? Now what?
The next one's super easy too. Queen of clubs. Probability of that.
That's all right. So it's probability of queen and it's clubs. Well, how many queens of clubs are there?
1.
Huh? 1. So it's 1 over 52. Okay, keep going. Now it gets a little more complicated.
Yeah, it's like queen union club, so I guess
All
like
right.
queen or club.
Probability of a queen or clubs. I would draw this out with a Venn diagram just to keep your head on straight. So if you think about this, here's my S. That's all possible values of the cards, all 52 possibilities. Then queens, I have a small little subset here of queens. And then I have clubs, and I've got a much bigger thing of clubs. I wish I could draw those symbols. If I felt confident, I'd try, but my penmanship has been horrible. With me? Now, when we do this, we're looking at the probability of a queen or a club. Now, here's where a Venn diagram helps. Remember the area adjustments, because what we can do is think of ratio of areas for this one. What we're looking at is this area right here. All that, right? Now, hear me. That's the probability of a queen plus the probability of a club minus the probability of a queen club. Y'all with me?
Because that's the repeat, right?
Yeah, and if you think about this, we can call that A, and we can call that B, and this would be A intersect B right there. This right here. I hope you can see it.
Yeah.
So that probability of a queen and a club, but that's my club symbol. Well, the probability of a queen is going to be what, 4, or really 1 over 13, right? Then it's plus the probability of a club, which is 1/4, and then it's minus the probability of the queen of clubs, which is 1 over 52. I hope he has something to that. And I guess the common denominator would be 52, so that'd be 4 minus 13 or plus 13 minus 1 over 52, correct? What is that? That's going to be 1652. Does he have that answer? Or 4? What is it?
13.
413. Is that what he has?
Should be.
That's what chat said. When I was
Chat. You don't get some wrong answers unless they've corrected.
Yeah, I don't see the solution.
Is that right?
I don't see the solution for 1.7 on the one
I'm sorry.
He
The
says it's not
solution
all.
for 1.7 is not.
Yes.
Yeah.
I'll put them all up. Can you send me a message?
That's definitely right.
What? I know, but send me a message and I'll make sure I do this. I don't know if this. Do you guys have access to solutions online somewhere? I mean, a lot of students have access to all the solutions I have. Usually if I don't have, I ask them and they get it.
No, I never look up the solutions online.
I have no clue, yeah.
Don't ever be in a court of law. You're laughing like that. I mean, doesn't look like a good witness. What gave him away? All right, you all with me? All right, now I want to get. I go to 11, so I got a few minutes. Okay, I wanted to just tell you, I kind of moved through this chapter fast, and for a reason. I think it's very simple, but there are certain, like, you know that crazy problem 5, the wording on it gets you? There's some stuff in there you gotta get straight in your head. You have to understand what he's asking and why he's asking it, because the way he makes statements isn't the way you're used to talking. And that's just natural with mathematics. So now, I had a ball doing some of this stuff. Love it. I'm not going to do that one. Okay. Next, I put up some notes that I think Bashir talked about last time. I want to talk about the next chapter's conditional probability. I'll give you a few more problems out of this chapter, out of chapter 1. Honestly, chapter 1 is not bad. It's just being familiar with the terminology and understanding how to get probability. And I'm going to go on with this. And now we're talking about chapter 2, which is conditional probabilities. And for this stuff, I like to do a whole lot of things. So there are things that are called disjoint or independent, where one event has nothing to do with the other. And then there are things where events depend on one another. And even though in the book, in Bashir stuff, he makes this kind of too complicated. We start with a real simple one. So when I'm talking about events, I like to use Venn diagrams because just understanding the geometry of the area relationships will give you the probabilistic relationships as well. So if I take a look at a set of all possible values here, doesn't matter what they are, and I say I'm going to represent one set A here, and I'm doing it with an area that it's trying to be proportional to the number of that in that set, all right? The number of items in a set can be specified all sorts of ways, but with a Venn diagram, it gives you a visual. That's the thing I like about it. Then there's going to be some B. Both of these have different items, and they have some in common. And they're within all possible values of the set. So if I want to know the probability of A, and the symbol for given B occurs is this. It means I'm looking for the probability of whatever I define as event A, given that event B has occurred. That's the idea. So when I look at this Venn diagram, this is something you have to look at and then reason through. He's saying B occurs, right? All of a sudden, the ratio of areas changes from the ratio of A to the S area. If I'm looking at the probability of A, and I'm thinking about the proportionality, he talks about it as frequency and numbers, but I'm saying if S is somehow proportional to all values possible in the set, and A is proportional to the values of the subset, and they're all equally likely in this case, then the ratio of area A to area S would be the probability of A. Does that make sense? And likewise for the probability of B, it would be B over S would be the probability of just B alone. But if A, I'm looking at the probability of A given B occurred. So it says B occurs. Now the area ratio business changes. In Bashir's notes, he talks about it as a frequency, but don't worry about that. Frankly, you're visually looking at that. That cross-hatched area right there is something that did occur. Now I want the probability of this occurring also. So if that occurred, what is the probability of this occurring? Y'all with me? Now listen, think about it. Well, if B occurred and I want that, it's the ratio of that purple area to the total green area.
Yeah.
All right, so what is this going to be? Well, the probability of the purple area is really going to be A, right? And it's going to, and you can call it P of A, and it would be intersect P. Can you all see that the way I did? And over what? Probability of B. Follow me? That would be, if you think about it, that because it's an area, I'm trying to show you the relationships with areas, and let me see if I can find where this is. Oh, wait a second, this is on page 29. But what he does, I'm gonna say this thing. He's going to call this right here, I put the intersect here, he'll just call it P of AB. It's the overlap area over P of B. I like this way better, but he does it that way. And do you all have your books here? You have a book. You have a book? Can you see on page 29 what I'm talking about there?
It's 2.1.
Yeah, and if you look on the next, on page 30, he puts an inequality down there on the very first formula. But the best thing to do now is probably a problem or two. Well, hold on. I have notes. This is called Bayes' theorem. It's Bayes' conditional probability. There's a lot of different ways to write some of these things, and it gets really complicated. I think we should probably just do a simple problem at this point. By the way, you're going to see some crazy stuff happening. Look at page 40 if you have a text, and you'll see the diamond networks he's going to get into with some of this stuff. Hold on. Okay, so on top of page 32, we're gonna talk about some of those things. It says a roll of an ordinary six-sided dice. That's the thing happening as observed, and assume each is equally likely. And then it gets. This is on page 32. The top A is 1, 2, 3. Just let's talk about this one. So for that problem, he gives you a dice, a single dice, a die. And you have possibilities of 1 through 6. And so for A, its values are 1, 2, 3, right? What is B for this one?
3 through 6.
3,
3, 4, 5,
3, 4, 5, 6.
5, and 6. Okay. And what is C?
1, 5, 6.
1, 5, 6. Now he's saying it's equally likely, and he asks for what? The probability of. We might as well just do them right now. P of A. What is P of A? If there's 6 events, that has 3 members, right? It's 1/2, right? What is the probability of B?
4, 6.
2/3.
2/3.
2/3, right? And what is the probability of C?
1/2.
1/2. Okay. Now, I'm going to do a Venn diagram here. Wow. This is my S, it's no longer square. Here's A, here's B, and here's C. Okay. And then just a representation, give you a visual image. And now he's going to ask for some stuff. So, go ahead.
Looks like A union C given B.
Probability of A union C
Yeah.
given B. Okay. All right. He says B occurs. You all with me?
Mhm.
Just take a moment before I move on. I want to make sure I don't mess with anybody. With me?
Yep.
All right. So first, here's my B. Just make sure. He says B occurs. So this has happened. Right? And he wants the probability of A union C. Well, what is A union C inside that green area? Not everywhere, but just inside that area. Well, A is here, and C is here. So A union C would be right here, because it's a union, right? Y'all see what I've done? Can you see it? Yeah.
Why wouldn't it just be the middle part where A and C are?
See that union
It's
operation?
intersection.
Yeah.
It's like or like a
Union is an OR gate.
Oh, that's right. Okay.
All right, so it's either of those. Remember, when it's the union of something, it's both of them. Everything overlaps. Now, if you look at this from an area point of view, think about it. If I want that, what would it be? Here's the way I'm going to do this. First, I'm going to say, since B occurred, I know probability of B is on the bottom. With me? I know that one, so I'm going to say, this over here, and I could just write B in a sense, and we could interpret the problem. Now, what about this? Well, here's what I'm going to take A right there, union B, and then I'm going to take A union C, and then subtract from that A, because now I've counted this twice, A union AC. A union ACB. Pardon me. Does that make sense to everybody? I'm trying to do this in myself. When I take a look at this, A union B would be this area.
Or that's intersect.
Or intersect, sorry.
Yeah, you're right.
Probability of A intersect B. And then this area would probability of
C intersect B.
C intersect B, that's right. You're right. Minus, and I'm going to run out of space here, but it'd be the probability of A intersect B intersect C. Make sense? Now you put the values in. Some of the stuff you wouldn't even need, it's too small a set to really worry about the Venn on this one, but if you take a look at this, the probability of A union C given B would be therefore, all right, let's start with probability of B is 2/3, right? Put it down there. And then the probability of A union B, intersect B, A
1/3.
and B, let's see, what do they have?
3.
They have 3 in common, right? So that'd be 1/6, is that right, class? So they have 1/6, and then it's going to be plus C intersect B, and that's 5 and 6, so it's going to be 1/3. You tell me if I'm wrong. Minus, and then it's the intersect of all of them. So let's see, what do we
I
got?
don't know if there is one.
3. No.
0.
Yeah,
It's 0,
That's the
so
null set.
looks like it's a 0 to me. So that's going to be what? So that's 2 plus 3 is going to be 1/2, right? over 2/3, 3 over 4? It's gonna be
Yeah.
3/4. Is that the right answer in the book?
Yes.
Sure is.
Okay, but you understand the reasoning behind it. Now, the Venn on this one maybe wasn't necessary, but you'll see when larger set sizes, when you get all sorts of crazy things in there, this is valuable to have that imagery in your mind. That's one of the things about the Venn diagram. Now, with conditional probability, let me just finish here. I know I'm over, but I'd like you to read for Wednesday, and I'm going to give you problems. Read through in chapter 2 on page 29, and read through, I want to get you through that. Now, some of this gets hairy. I want you to get through page 41. Some of that, it'll set you up. A lot of times what I want you to do is have questions formed in your mind when you come, because some of this stuff's going to get really, really crazy. I'm just leveling with you. If anybody's ever had this before, and either dropped or whatever reason, you're taking it again, one of the things you probably realize is you didn't have a correct estimation of the amount of time it takes to learn this stuff, to really understand it. I trust you on this one. There's some really, really bizarre stuff that happens. I'm doing my best to explain it simply, because if I put too much complexity up here right away, I don't think you guys will benefit from that. Okay. Who's in my EMAG class? You're in the EMAG. Who else? You? Who else? You are? Okay. I got to check on it right now. I want to check on how many people come in this class. And if you need to see me at my office hours are right after this one. Right upstairs. Did you understand that? Did it help? I'll go into a lot more theory if you want to, but I mean, some of this stuff gets kind of hairy.